Let's talk about neutralization reactions. You already know that an acid plus a base yields a salt plus water. That's a neutralization reaction, especially if you got your Arrhenius acid and your Arrhenius base. So how does this help us do anything? Why would you want to neutralize? Well, one, if you burn yourself, you obviously want to neutralize that reaction. You want to stop that thing from reacting. But number two is what we call a titration. So titrations are this beautiful thing in chemistry where if you react an acid and a base, and one of those is a known value, a known concentration, and the other one we don't know a lot about it, you can use a titration to find out more chemical information for the properties for the chemical that you don't know a lot about. All right, so this is used all over the place, and metal analysis, groundwater analysis. I mean, I could just keep going. There is so many applications for titrations. And so I want us just to use this right now and do a couple practice problems and see if we can't figure out how a titration works. So first off, when you're doing a titration, what do? You take a burette and you fill it up with a sample that has been standardized. Standardized means you know something about it. And so in this case, we know the molarity of the titrant. Okay, the thing that we're titrating with is called the titrant, and you know something about it. And so in our case, for our first example, we are going to react hydrochloric acid plus potassium hydroxide to yield water and our salt, potassium chloride. And so in our case, we know something about our potassium hydroxide. So that's going to be in our burette, and it has been standardized. How has it been standardized? Well, we know that we have a 0.15 molar solution. So that's moles per liter, okay? And we're going to use that to find out what is our molarity of hydrochloric acid. And so what we do is we put a known amount of our hydrochloric acid, and in this case it's going to be 15 milliliters of hydrochloric acid. We're going to put that into an Erlenmeyer flask below the burette. And then also with that, we're going to put an indicator. And our example, for most of our reactions, we're going to use something like phenolphthalein, which is just simply a colored dye that when it's at 1 pH, it's going to be one color, and whenever you change its pH slowly with time by adding something like potassium hydroxide to it, making it more and more basic, you're going to change the color. And so phenolphthalein is really a neat indicator, and we're going to use it in our lab this semester, but it's clear when it's acidic. So when you only have hydrochloric acid mixed with it, it's clear. But then as you add potassium hydroxide, you're going to slowly put drop by drop by drop, and then all of a sudden it'll be a pink solution. And that pink solution means that you have gone one drop past that neutralization point. Because at neutralization point, you're assuming that the moles of my acid equals my moles of my base. And that's a huge, huge fundamental principle. I'll write it up here. Moles of my acid equals moles of my base, where this N is just a symbol for moles. And so this statement is true, and you'll hear me say it so many times, at equivalence. Okay? So at my equivalence point, that point right when that color change happens, that is going to be where your moles of your acid plus your moles of your base, they're equal, okay? Because now at that moment you've got water. But the second you put one extra drop in, that's where you're going to get that basic complex, and your color change of your phenolphthalein is going to now turn pink, okay? And so at equivalence points, your moles of your acid equals moles of your base. Your indicator is something that just happens to change colors right at your equivalence point. Okay, so that's a huge concept, which we're really going to get into in lab. But just for the sake of lecture, just know, at your equivalence point, moles of acid equals moles of your base. And because that's true, whenever I do a titration, I can say, all right, I'm going to use my potassium hydroxide to titrate hydrochloric acid. How many milliliters did it take to make it pink? And at that moment, my moles of my acid equals moles of my base. And now I have everything I need to solve, because I'll have a moles of potassium hydroxide, I'll have a volume of potassium hydroxide, I'll have a molarity, and therefore I'll have a moles of hydrochloric acid. Let's see how this all plays out in a real problem. Okay, so back to this. So I have 15 milliliters of hydrochloric acid inside of my Erlenmeyer flask underneath my burette. In my burette, I have potassium hydroxide, and I know it's 0.15 molar. So I'm going to slowly start dripping it. I'm going to swirl it as I go. And then once it turns pink, I stop the stopcock and I record exactly how much volume it took to go from clear to pink. And that volume in today's example is going to be 17.50 milliliters. All right, so using just this data now, I can figure out how much or what the concentration is of my unknown, which is my hydrochloric acid I have in my flask. All it is molarity conversions. So remember, you know molarity equals moles per liter. This is super important in these problems. These two pieces right here are what make you so you can solve these problems. So let's do them together. All right, so we start out here. Start out with what you know the most about. So in that case, it's our molarity. So we have 0.15 molar potassium hydroxide times my volume. Now remember, molarity is moles per liter, so I need to put my milliliters into liters. 0.175 liters. And that's going to give me a total number of moles of 2.625 times 10 to the negative 3 moles of potassium hydroxide. All right, so now I've solved for moles. How does that help me? Well, I know at that moment where it turned pink, my moles of potassium hydroxide equals my moles of my acid. And so in this case now I know that I have 2.625 times 10 to the negative 3 moles of HCl, hydrochloric acid. If you wanted to, you could have done a conversion factor, 1 to 1. Okay? So now we've got moles of hydrochloric acid, and I will say it's 1 to 1 because of the balanced chemical equation. Okay? But at my equivalence point, it's 1 to 1. All right, so we've got moles of hydrochloric acid. Now, can I turn this into molarity somehow? Absolutely. So we take our moles and we divide it by our volume, making sure that we once again turn that into liters, because I have my 15 milliliters and I'm turning this into liters. And now I do my math, put that into my calculator, 0.175 molar, which if we correct for our 2 sig figs here at 15 milliliters, that equals 0.18 molar hydrochloric acid. So I just used a known standard to figure out the concentration of an unknown solution. And so this is just one example that's going to kind of walk you through how do we do a titration problem. So for our second example, now we have potassium hydroxide reacting with sulfuric acid. Remember, anytime you have a strong acid or a base, it's a single arrow. All right, for this equation, it's going to get a little more complicated because we have a diprotic here. Okay, so there's 2 protons that could potentially come off and react with potassium hydroxide. To simplify things, we're just going to do what's called our first equivalence point, which means we're going to assume that all of these come apart. So you've got your potassium, your hydroxide, but we're going to assume only 1 proton comes off. That's your definition of a first equivalence point. So 1 proton comes off. So if 1 proton comes out of this, you've got H plus, and then you have HSO4 minus remaining, okay? Because if you take away 1 positively charged, you're going to get 1 negative left over. Or another way of thinking of it, if we reattach it, your positives and your negatives cancel out to be neutral. All right, so this is what we're looking at, because now these can form water and these 2 can react to form our salt. All right, so to finish out this equation, and so notice we're super simplifying things here for titrations. 1 to 1. Titration is always 1 to 1, okay? You're not going to ever have to worry too much about balancing because we're simplifying it here for you where your moles of your acid always equals your moles of your base, 1 to 1. All right, so what do we do here? Yields water plus potassium ions plus HSO4 minus. And you can leave it like that, or you could put like KHSO4, okay, whichever one you prefer. So now that we've got our balanced equation, let's set up our problem. What are the parameters that we're going to work with today? So in this case, we have potassium hydroxide that we know 2 things about. It is 1.50 molar. And then we also know that it's going to take 35.55 milliliters to titrate our sulfuric acid, which means potassium hydroxide is going to be our titrant. It's what's in our burette. Whereas sulfuric acid is going to be in our Erlenmeyer flask, and it's the thing we're trying to find something out about. So what do we know about it? This time, instead of knowing the volume, we know its molarity. So we know it's 0.0500 molar, and we're asking the question of what volume do we have within our Erlenmeyer flask? And so using this and knowing our two pieces of our equation, that molarity equals moles per liter and moles of acid equals moles of your base at your equivalence point, we can solve. So the first thing you do is start with what you know. So in this case, we know 1.50 molar of potassium hydroxide, and we also know its volume. So if we can do those two pieces of our puzzle, we can find the number of moles. So we've got, turning it into liters, 0.3555 liters equals our moles, which is 5.3325 times 10 to the negative 2 moles of potassium hydroxide. So we solve for moles using molarity and volume. Next, we know our moles of our acid equals moles of our base. Therefore, we also know our moles of our acid, which is sulfuric acid. So we've got 5.3325 times 10 to the negative 2 moles of H2SO4. We also know its molarity. So 0.500 molar. We'll solve for X. Bring this molarity under, bring the X out here. You're able to solve for your volume of sulfuric acid. So what is it? Our final volume is 0.107 liters, or 107 milliliters of sulfuric acid. And that is our final answer for this titration problem.